Let us see one of the other properties of matrix. This property says, which is also called one of the theorems of matrix, let's call it as Theorem 1. If A is a square matrix, let's take A with any particular set of numbers 1, 2, 3, -3, -2, -1, 4, 5, 6. The order is 3 by 3 and hence it is a square matrix with real numbers. All these numbers are real. Then A plus A dash is a symmetric matrix. Let's call this as B. Let B be equal to A plus A dash. We are given that if A is a square matrix with real numbers, then B, if B is equal to A plus A dash or A transpose, then B has to be a symmetric matrix, right? Similarly, we are also told that A minus A dash is a skew symmetric matrix. So let's call this as C equals to A minus A dash. Then according to this theorem, C has to be a skew symmetric matrix. Now before we do anything, let's find out the value of transpose of A. As we've been discussing, how do you get the transpose of matrix? These are the rows of A. To get transpose of A, we simply convert the rows into columns. So you've got 1, -3, 4. Then you've got 2, -2 and 5, which is your row 2. Then row 3, 3, -1 and 6. Right? Now once you've got these two numbers, you can find out B, right? So B is equal to A plus A dash. So if you try taking the sum of both of them, you'll get 1 plus 1 equals to 2. -3 plus 2 will give you -1. 4 minus 3 will give you 4 plus 3 will give you 7. Sorry, it's not minus, it's plus. Right? 2 plus -3 gives you -1. -2 minus 2 gives you -4. 5 minus 1 gives you 4. 3 plus 4 gives you 7. -1 plus 5 gives you 4. 6 plus 6 gives you 12. Right? Now if B is a symmetric matrix, then B dash should also be equal to B. Let's find out B dash. So if you find out B dash, which is the transpose of B, then what do you get? You get 2 here, you get -1 here, and you get 7 here. Basically converting first row into first column, then second row -1, -4 and 4, and then the third one 7, 4, 12. Right? Now if you notice, both these matrices are equal, hence B is equal to B dash, and if that be the case, we know that B is a symmetric matrix. Why? Because B dash is equal to B. Right? Can we try and prove that this is also true? Let's try it. Okay, let's say we take a transpose of both the sides. So we get B dash is equal to A plus A dash transpose. So we say this is A transpose plus A transpose transpose. I mean, you've put in A transpose here, then A dash transpose here. Right? This is because if you remember, A plus B transpose is equal to transpose of A plus transpose of B. This is what we learned in some of the previous lessons. Or you can write this as transpose of A plus A. Why? Because transpose of A's transpose is A itself. So we say A is equal to A transpose transpose. Right? Or you can also write this as A plus A transpose. You've just changed the order. Why? Because we know that A plus B is equal to B plus A. Hence, transpose of A plus A can also be written as A plus A transpose. Right? Which is what? Nothing but B. So we conclude that transpose of B is equal to B, which we've already seen kind of through this example. Right? Now let's see the second one. C is equal to A minus A transpose. C is equal to A minus A transpose. Right? Again, let's take the transpose of both the sides. So we get C transpose is equal to A transpose minus A transpose transpose, right? Or A transpose minus A. And if we take a minus common out here, we can get this as minus A dash plus A. But A or minus A minus A dash, which is nothing but C, right? This is what we have taken here, minus C. Hence, this becomes a skew symmetric matrix. Now you can try the solution of this at your own end using the numbers from this particular matrix. I'm not doing the resolution for this one. Try it at your own end.